So we use something called as turbulence model. So you might have heard of K epsilon, K omega, SCA models, and then what else? LES turbulence models, correct? Or SST, sure. So these are called as turbulence models. Now you need to understand that whenever you see the word modeling, and this is something that I tell in all of my workshops related to CFD, whenever you see the term modeling, that means whatever is before that is being approximated. So if it is turbulence modeling, you're approximating turbulence. Now, why do we do this? Well, when you approximate the turbulence, you can expect to get your simulation results in a shorter manner. If you want to solve it 100% accurately, you need to use like very, very detailed turbulence models like K omega SST in this case. But that is going to increase the simulation time a lot. The other thing that you need to understand is cavitation modeling. Now, one thing that you all need to remember is when MRF approach is used, when multiple reference frame approach is used, or moving reference frame approach is used, your cavitation predictions will be wrong. Okay, because when you think of cavitation, these are bubble formations, right? These bubbles, when you look at your impeller, so if I draw a very simple impeller, something like this. So in general, cavitation takes place at the tip of the impeller. Now, if you look at experimental data, the vapor formation bubble is not symmetrical, meaning in one impeller it will have a different shape, in the other impeller it will have a different shape. This is basically an interplay of geometry and turbulence, right? But when you use MRF approach, you are kind of having the same source term, right? So one thing that is very common is that your cavitation bubble will be very, very symmetrical. So there is a possibility to underpredict or overpredict the cavitation in case of the MRF approach. So if you're interested in cavitation, for example, if you want to do a centrifugal pump simulation for your final project, if you want to predict cavitation, if you want to show cavitation, that would be a very nice project. You can also publish the data in a local conference. So if you're interested in doing something like that, don't use MRF. You need to use something like transient solver, something to keep in mind. As we have all discussed, cavitation is bad. It can cause damage to your impeller. Now, how do we know if cavitation is captured computationally? How can we determine that? Does anyone have any ideas? From a simulation point of view, what should be the data that I need to look at? The answer is very simple. It's not velocity, it's, yes, density is one, pressure is the other guy. What you can do is you can just look at pressure, and then what's going to happen is wherever cavitation occurs, your pressure is first going to drop. Now, sometimes people don't have a cavitation model, meaning there is no mathematical model that approximates cavitation. So what they do is they basically assume that everything is filled only with water, which is called as an incompressible flow simulation, because everything is filled with water. And when you run the simulation in certain areas, the pressure will drop, and you manually look at this pressure and you will see if this pressure is lower than the vapor pressure or not. How will you know that? Well, I can use some kind of a data book and I can figure out what the vapor pressure is. And I can identify that, okay, in these areas, my pressure is lower than vapor pressure. And that is where cavitation would occur. So this is the first level of prediction. But the problem with this approach is you are not able to see the cavitation bubble. The second approach is using a cavitation model. So what the cavitation model does is when the pressure drops below the vapor pressure, it takes a particular amount. It takes that fluid and converts it into a vapor using an empirical model, meaning it uses a mathematical model that was developed by experiments, and it converts the liquid into vapor according to that equation. And this vapor is basically a new species. So you create something called as a water vapor species, and this water vapor is transported throughout your centrifugal pump, and that is basically your vapor bubble. If you do the simulation, you'll be able to see how those vapor bubbles are formed and how they are being stretched and how they interact with the surfaces. But the vapor pressure is temperature dependent too. Exactly. That is why you don't look at vapor pressure. Okay, so basically this is the equation that I wanted to show you. So in addition to your Navier-Stokes equation, guys, you actually have a void transport equation. So alpha is your void fraction. And those of you who are in our CFD course, you can see that this equation is very similar to pretty much any other equation. You have a time derivative, And then you have your convective derivative, which is nothing but divergence of the scalar multiplied by the velocity vector. And then on the right hand side, you have source terms. So here, what you're basically doing is, this equation basically solves for a parameter called alpha, which keeps track of the voidness. So voidness, if voidness is 1, that means that particular computational cell contains only gas. Which gas? The qth gas, the qth phase. Q is the number. If Q is 1, that means you just have 2 phases. If Q is 2, then you have 3 phases. All right. Actually, let me take it back. Let us put it simply. If Q is 2, then you have 2 phases. If Q is 3, you have 3 phases. All right. So this equation will basically help you understand how your bubbles are formed. And you solve it along with your CFD equations.